Hello everybody. Today we'll be looking at what we can do with a graph of velocity for a pendulum as it moves back and forth. The first question asks about the length of a pendulum. We ought to be thinking here the length of a pendulum is related to the amount of time it takes to complete one oscillation. That information is something that we can figure out based off of this graph. So the amount of time for one oscillation is the time for one between two identical points on the graph. So for example, from a high point to another high point, this would be the period, capital T. And so on this one, it looks like the period is about 1.6 seconds. So for the length of a pendulum, we have an equation to calculate the length of a pendulum based on the period. The equation that's written on your equation sheet is Tp, the period for a pendulum, is equal to 2 pi square root L over G. And there is this note here that we are assuming that it's on Earth, so then we know G will be 9.8 meters per second squared. T from the graph is 1.6 seconds, and so we're looking for L, and this is all for part A. So I can rearrange this equation to solve for L. I get Tp over 2 pi, and then I'll, whoops, not square root, but square both sides. Square both sides, and then multiply by G, and that gets me L all by itself. And so I can plug in for each of those values. So I have 1.6 seconds divided by 2 pi squared times G, which is 9.8 meters per second squared, gives me L. And so for L, I get a value of 0.635 meters. So pendulums, it's only length and the acceleration due to gravity that influence the period. Second question, write an equation for the velocity as a function of time. Okay, so this is back to the graph. Velocity and position and acceleration and force, for all these simple harmonic motion types of things, we're going to see are sinusoidal shapes, so either sine or cosine. On this one, since we start at a high point, it probably makes sense, so I start up here at a high point, it probably makes sense to have our graph be a cosine curve, but it probably doesn't make a huge amount of difference here. It's the same shape either way. It's just shifted one way or another. But this one, we'll write it out as a cosine graph. We need to make sure that it's repeating itself after 1.6 seconds, and we need to make sure that it shows a maximum velocity of, it looks like about 2.2 meters per second. So let's kind of collate all that information here. So for part B, we'll say Vmax is 2.2 meters per second. The period still is 1.6 seconds. So if I'm going to guess that this is a sinusoidal shape, or really we know it's a sinusoidal shape, here we said it's a cosine shape. Since we start with the maximum value, I can say that the V as a function of time is going to be equal to some constant, and I'll just call it P, times the cosine of some other constant, I'll call it Q, times the period. Now P is the constant that's going to be multiplied by cosine to make it so that our velocity value has the correct maximum value. Cosine by itself has a maximum value of 1, so if I want to have a maximum value instead of this 2.2, I need P to be 2.2 meters per second. So velocity as a function of time then, I know is going to be 2.2 meters per second times the cosine of qt. So I still need a value for q, just as we did with the position functions here. We can say that when t equals 1 period, or 1.6 seconds, we need our cosine function to start repeating itself. Cosine function starts to repeat itself when we get to 2 pi. So we need here q times 1.6 seconds to be equal to 2 pi. And so 2 pi divided by 1.6 gives us our value for q, which is going to be 3.93. And the units on that would be 1/seconds. So then I can write my velocity function as 2.2 meters per second times the cosine of 3.93 per seconds, that's the units there, times t. Now, part C asks us basically, is this actually simple harmonic motion? We make that small angle approximation for a pendulum to make it work out so the restoring force is proportional to distance from equilibrium. So here we're asking, is that a valid assumption to make for this case? Which basically means, are we at less than 15 degrees for our amplitude? To figure this out, we need to understand that when we're at that amplitude position, this pendulum system is going to have, the pendulum in an Earth system is going to have a maximum value for gravitational potential energy and a 0 value for kinetic energy. When that pendulum gets back to equilibrium, it's going to have a minimum value for gravitational potential energy and a maximum value for kinetic energy. So basically it's going fast when it's low down, and it stops when it gets to its maximum height. So we're going to look at how much kinetic energy it has at a maximum, and that'll be the same as the amount of gravitational potential energy it has when that's a maximum. Now, once we figure out how much gravitational potential energy it has, we can also figure out how much higher it must be than its equilibrium position when it's at its maximum, when it's at the amplitude spot. From there, we'll be able to tell what the angle is, and we can evaluate whether it's 15 degrees or less. So, on part C, we're going to say that our gravitational potential energy at the amplitude position is equal to the kinetic energy at equilibrium. And so this will be equal to mg delta y, and this side will be equal to 1/2 mv squared. Got a mass on each side, so I'll divide both sides by m to get those to cancel out. And then I'm looking for this value delta y, so let's divide both sides by g to get delta y is equal to v squared over 2g. And here we're talking about our maximum speed. I should make a note there. So our delta y is going to be equal to that 1.6 meters per second squared. Actually, that number's not right. I think it's 2.2. There we go. Okay, 2.2 meters per second this time. 2.2 meters per second divided by 2 times 9.8 meters per second squared, which is going to give us a maximum height of 0.247 meters. Okay, now how does that relate to angle? Well, this one I think we ought to just sketch out. So we have our pendulum, and at one moment it's going to be hanging straight down. And what do we figure out for the length of the pendulum again? 0.635 meters. Okay, and then at some other moment in time, it's going to be hanging off to the side like this. We'll have still the same length, 0.635 meters. Now that's off at an angle like this. And then we'll also have that the Y position has changed here by 0.247 meters. Not quite to scale. Oh well. Okay, so then on this graph, I think it makes sense now to look at this little triangle that I can draw in, which will make a right triangle, and we'll have this be our angle theta that we've pulled the pendulum back to. And I'm going to give this a value, let's call this Z. So that we can just kind of make a note here that this value of Z plus this 0.247 has to add up to this total distance of 0.635 meters. So I can use that to figure out what Z would be. So now Z is going to equal 0.635 meters minus 0.247 meters, which is going to be 0.635 minus 0.247, 0.388 meters. Now I know two sides on that right triangle, and so I can find the angle. And the sides that I know are the adjacent side to that angle and the hypotenuse. So I'll be using the cosine function. Say cosine of theta is equal to the adjacent side, 0.388 meters, divided by the hypotenuse, 0.635 meters. So now theta will be the inverse cosine of 0.388 meters divided by 0.635 meters. And so theta is going to have a value of 52 degrees. Okay, now that 52 degrees, that is greater than 15 degrees. So this actually isn't simple harmonic motion. Doesn't fit well with that small angle approximation idea. So we are at this point finished with this problem. These simple harmonic motion things, they can really involve quite a bit. So we have some of the more obvious stuff like the period of a pendulum going on in these, but then also things like the conservation of energy, even some fairly complex trig can be brought into these problems. So just kind of keep in mind all the different things that you see with simple harmonic motion, the things that we see being drawn into this, because you never know what you're going to need to pull out of this. The other thing to keep in mind is that these graphs really provide us with lots of information. So on this one I ended up just using the time between two identical points, the period, and the maximum velocity. The mass of the bob was given to us. We actually never even used that information. The only time mass ever appeared was in the energy equation, but it canceled out there. So actually this entire problem could have been done simply from this one graph. So as I said, lots of information there. Keep that in mind as well. Thanks very much for watching. If you learned something, please click like, or if you think you might learn something from the videos in the future, go ahead and subscribe to the channel. Thank you again.